So this is the second part of the attractor dynamics lecture about vehicle movement generation. And we've called this the sub-symbolic approach. Last week, I clarified that it's really more about being reactive, that is to the sensors that inform you locally. And there's just some conceptual difference, and that's something that I will be elaborating today. So, where's my cursor here? So last time I talked about behavioral dynamics as this dynamics of obstacle avoidance. So the notion is that if you have a vehicle and it has the heading direction that's as this dynamic variable against some arbitrary world axis, right? Then you can express constraints like going to a target or avoiding obstacle as values, desired or undesired values. That's a very general feature. Almost all approaches to vehicle path planning conceive of things this way, that some steering angle or some control variable has desired and undesired values. And in that, so we did this dynamic system. We'll see the same dynamic system again today. And in this conception that I talked about previously, these were discrete different values. You had a value for the target, maybe multiple targets. You had a value for each obstacle. So in some sense, there was a conception that these obstacles or targets were identifiable things. So the dynamic system, of course, is generates time courses. It's a time-dependent system. And then there would be, of course, the notion that if you look at a later moment in time, the equation is going to be the same or similar. And therefore that this is the obstacle I previously had as a term in my equation, and now it's still the same obstacle. I might have 3 or 4 obstacles. So in some, that's why I call it symbolic. So in some sense, it would mean that if you have some sensory system that obtains information about these obstacles, you would have to know, oh, this is obstacle number 1, and now I'm updating its value, and there's another obstacle, number 2, and that adds to my equation, and so on. This is actually routinely done by sensory processes that deliver information about that. For instance, for those of you who know this sort of thing, you would have Kalman filters, that integrate the current sensory information with previous estimates. And for every obstacle, you would have a Kalman filter. And if a new obstacle arises, you have to start a new Kalman filter. And there's a whole process of matching which sensory input is an update to which of your Kalman filters, and when do you actually have enough evidence to start a new one. Maybe occasionally you will close down one, and so on. And there are other approaches to that. And there's a whole field, computer vision, for instance, is a field that deals with creating instances like that, and so on. So that's a kind of complication that would arise. Sometimes, very typically, it arises for targets where you'd have to make decisions like that, what really your target is. For obstacles, it's actually not so obvious you really need that, because as I argued before, you really just need, this just summarizes what I just said. You could say, well, as long as I know in which directions to be cautious or which directions to avoid, it doesn't really matter. Yeah, I'll skip that. It doesn't really matter if these are different objects. Ultimately, two things are two obstacles if you can drive between them. And if you can, then you might as well consider it one obstacle. So it's really a question about directions of free passage. And so I'll present to you a version of this approach that doesn't need that categorization, that just uses sensory information and still uses the same mathematics. And it works very well. We developed this approach when I was in Marseille, building low-level robots. Our goal then was actually to get rid of all this high-level perception, which we did when I developed this earlier here in Bochum, and then moved to Marseille, where we had much less money, for instance. We wanted to build very simple robots, very cheap robots, one of which was a Lego robot, before Lego robots existed. But it was technically sort of like a Lego robot, which, the Mindstorm is a Lego toy you can buy these days and program this robot. So we actually used exactly that chip. I'll show you later an example. And so there was the idea, can we do this with low-level sensors? And this connected, of course, to this topic of behavior-based robotics that I mentioned in the introduction, that will be that you have sensor information that is useful for the particular behavior you're looking at, and not And you don't necessarily have to have a world map for every being. Now, optical avoidance function just needs a depth map, some estimate of where there are things that are close and thus dangerous. It doesn't need many other kinds of information that you might need, for instance, to decide about targets or to classify objects in the world as pedestrians or as other things, traffic signs and so on. These would be much more demanding kind of tasks. So in Marseille, the person who really drove that forward was Stella Bicho, the Portuguese professor. She's now a professor at the University of Minho. She then was my doctoral student and performed that work in Marseille, but then she got a degree from that Portuguese university. And I will be using her doctoral thesis, where she elaborated these things more than in some of our published papers to illustrate some of the ideas. So the concept is that you would have a vehicle, this is still the same kind of vehicle, that has a limited number of sensors, and they're real just distance sensors. So each of these red dots designates a distance sensor like that. And they give you some sense of whether there is something close, what the average distance or some measure of distance is within a certain cone of sensitivity of these sensors. I'll show you examples of that later. And that for each of these sensors, you would erect a repulsive forcelet in the direction in space into which the sensor is pointed. So treat it as if there was an obstacle there, and use the measured distance to modulate the strength of repulsion from that direction. That was the very simple idea. So in, I think I have a picture. I'm not sure where it is. Yeah, I have it a little later. So the example that we'll be looking at in more detail, the sensor was actually some uncalibrated distance sensor. It was a infrared light emitter and detector. That is, you would be sending an infrared light beam out, and that has some spread, and then just detect the amount of light of that frequency that is being reflected. And that reflectance would be somehow reflective of how far the surface is away from which it's reflected. So if very little light comes back, there is no surface within the maximum range of this sort of sensing, which was very close, like one vehicle size. You would no longer get a useful signal back. If there's some surface within this cone in which this light beam was focused, you would get a signal back. And the closer that surface, the more signal you would get back. Unfortunately, it also depends on the reflectivity of the surface. You know, if you get a very nice white surface, you get a lot of signal back. And also how much of the angular range is filled by that surface. If a thin leg of a chair, for instance, you would get less signal back, even though the chair could be close. So that's what I call uncalibrated. It's very crude ad hoc signal. And that was interesting to us to try that, to see if even a crude thing like that could work. You know, a laser rangefinder, for instance, would give you a calibrated signal. It's much more expensive, much more effort and so on. And these little sensor devices would cost not even a cent. We later built a wheelchair based on that. We had to buy 1,000 of those. And the 1,000 sensors cost, I think, €10 at the time, or 10. I don't remember. It was actually before the euro. It was like 4. I don't know exactly how much it was, but very cheap. And so you could use these a lot of these sensors if you want, but you have to pay the price. It's uncalibrated. In the end, you will see it actually worked surprisingly well. So that was the challenge that we posed ourselves. So the math of this is straightforward. I put this reference in the slides. You can actually download that thesis. I'll give you access to the relevant chapter of the thesis when I give you the essay. The essay will actually study that chapter of the thesis. It's also published, but the thesis is kind of nicer. So here I'll take you through this, and you will see there are a couple of issues. It works right out of the box. But then we have to think why it actually works. And I'll try to work through these issues. So a priori, the idea is very similar, right? Look at any sensor, like let's say which sensor that is, I don't remember. Any of those, this will be the sensor 5 and 6, whose contributions we're looking at here. And each sensor would have that shape, that force, that shape, that, you know, the contribution of the sensor to the dynamics. that would be, have a repeller, and the slope of that would be modulated by strength, by distance. So a sensor that gets a small distance signal would have a steep contribution, and thus the steepness will determine also this maximum. The range limiting factor was done here with an exponential. You studied that in the exercise sheet. Actually, I think you had it in last week. It's the same mathematics. So this amplitude is modulated by the strength as well, right? The slope determines that amplitude. And the width of this sigmoid, of this forcelet, would be based on some computation. I'll go into that. That takes into account the sensor range, or which range this sensor is detecting surfaces. And then you would just add that for these different contributions. So here's the mathematical formula that you just studied on the exercise sheet, I think, right? Was the previous sheet, right? You studied that equation. So this is the range factor. The width I'll have a slide on. This is the linear function. So because of this range limitation, we don't actually bother to put a cosine function in there, which will be theoretically necessary. You can even put a cosine function up here, but because the range is limited, it doesn't really matter. And by the way, you'll see that when phi, if you look at this is the angle into which the sensor points in the world, right? This is not the angle at which the sensor is mounted on the vehicle, right? That will be a constant, right? What phi minus psi is that angle at which the sensor is mounted on the vehicle, right? If you look here, sensor 4, I believe, is right in front, right ahead, and then sensor 3 is a little bit to the right. And let's say if you look at, let's take sensor 6, then it's points into this angle in the world, right? This angle here, oops, sorry. And the vehicle points in this direction, so phi minus psi, so minus psi plus phi, that's exactly that angle, right? The angle from the forward direction to the sensor. So that's a fixed number, right? For every sensor. Here it's 2 of those 30 degrees, and then for the other sensor it will be 1 of those, and so on, right? So this here, phi minus psi, is a constant for every sensor. And similar, phi minus psi is actually a constant. And so this is kind of shows you that the formal way of thinking with these dynamics helps us define this dynamics. But when you put this on the vehicle, these are actually constants. So you don't actually need to compute phi. You don't even need to know phi. Now, it's just there to understand why it works. Not surprising. The only way that the heading direction matters is that depending on the heading direction, you get different signals from the sensor, which will determine the strength factor, and we'll see in a moment also determines the width factor. But you don't need to explicitly know phi for obstacle avoidance. And one consequence is that the front sensor doesn't contribute at all, because the front sensor is mounted exactly in the direction in which you point, which the vehicle currently is moving. So that psi is equal to phi always, right? It's pointing in the world in the same way the vehicle is pointing. So this term is 0, that term is 0, so it doesn't contribute. We had people who did lab classes with us who didn't believe that. We just showed them that you can turn off that sensor and it doesn't change the road behavior, right? The front sensor does not contribute to obstacle avoidance. It's essentially neutral with respect to going around it on the right or on the left, right? It's forced to 0. We had that front sensor because we also controlled the speed of the robot. And for that, the front sensor was the most important one. And that chapter that you study has some explanation of that, about that, even though you don't need to study that in detail. Good. So the way that the sensors sensor information enters is through the strength, and the strength was by distance dependent, and we use this form. There's no reason why it has to be exactly that form. So an exponential decay with 2 constants. So the total maximum strength of that will be 1 constant, and the decay rate, over which rates you are sensitive to the change in distance. And we use an exponential scale so that this actually has units of length. So that's a good idea of how to control it. In practice, the problem is really that the distance that you estimate from this sensor signal is also a heuristic approach to calibrate how much light reflection you get as a function of distance. We tried that out in the laboratory. That is somewhat limited. You can imagine this infrared light disperses too much, and there's not enough reflectors to get it. In practice, the kind of sensors we had, this depends on how much emission there is, was able to sense about distances of about 50 centimeters max, maybe 40 centimeters. And the vehicle was about 35, 40 centimeters wide. And the one I'm talking about here, we have different versions of it. And so it would about be one vehicle length it would sense. That's the maximum distance. So it always drive up to anything up to that distance before it even takes the obstacle points into account. So that's clearly a local approach, right? And that's actually the spirit in which these reactive approaches are used today. For instance, I mentioned many of them actually use the potential field approach, which is not really better, but just maybe because it's more known. And that they typically just about that thing, that's about one vehicle size that you're using that. It's actually even true for these very primitive robots. A lot of robots only stop as obstacle avoidance, like in vehicle industrial contexts. And there's also typically about one vehicle size. If you have any of these robots, vacuum cleaners, you can play with that by stepping in front. You see it's actually a little bit less even than the vehicle size. And many of these are actually using infrared sensing in the same sense, in the same style. But they're also sensitive to how large the vehicle is. You can play with that if you have one. Right? Put a little narrow strip and you see it drives up closer to that. And you can even bump into stuff sometimes. Good. Now the range has a subtlety. So the range is first of all, of course, specified by the properties of the sensor. We actually put a little bit of rubber around the emitter so we could control how widely the light is spread, roughly. And then that was about, I believe it was about 15, plus minus 15, so 30 degrees approximately. Sensor range, but it's important that you take into account that you really want to avoid that whole sector. So the maximal obstacle that would exactly sample that angular range, you have to avoid that, which would mean that there has to be half a vehicle size on the left and half a vehicle size on the right that you also want to avoid. Right? Nice little circular vehicle. And that turns out to make the range distance dependent. So this is the formula, you can figure that out. Now the vehicle on the left and on the right will have a different angle depending on how close you're to the vehicle. For instance, if you're closer, the angular contribution of the vehicle will be larger. Actually, to the center. If you have to avoid this, I have to steer here quite a bit. Right? If it's possible, if it's very far, then it's the angle that I will suspend on my sensor surface as an object that projected at that distance is smaller. And that actually plays a role. So under some conditions, this will mean that as you get closer, the force that will be broader, and therefore will have more this fusion kind of behavior. That is, they will tend to make an average repeller at the center. So they will not promote so much having separate attractors, separate repellers with letting pass in between. In the implementation on this vehicle, as well as this chapter 4 of a thesis that was simulations around that effect doesn't show because the sensors are so short-sighted that at that distance, the size of the vehicle already plays a big role. It's already very broad. But we implemented, and actually, Lucas can show you this in the simulator, where you can emulate sensors that are much longer distance, and then it actually really plays a role. You can drive up to a wall and still consider that to be made from discrete samples, which you could drive in between. And as you get closer, they fuse. Good. And so all the different sensors just add up. their contributions, and then we just take the sum. And so this is a heuristic approach. You could also try to determine the exact way how you superpose these individual contributions so that the resultant attractor repeller is has certain properties. So that would be an exact approach. Now, review exact approaches like that in the survey lecture. But here we just add them. And so, for instance, in this particular configuration, only sensor 6 and sensor 5 get any distance signal within their range, and these are therefore the only 4 slats here, and there's some, as you see here, will erect a single repeller average between the 2 locations, so that would be an angle just about vertical here, and that's because these 2 contributions are broad enough for that, and then the resultant 4 slat you see has a range that is about approximate for an obstacle of this size. And that actually raises a question that I want to talk about now. Often I find that people hear the first time think, oh, that makes a lot of sense and so on. And but if you think about it a little bit, then you must say it's actually strange why that would work. Because this is not a dynamic system, it's not a correct dynamic system. This is the metaphor is this is like a donkey with a carrot. That's where the carrot is attached to the donkey. And then, as the donkey moves, the carrot moves. Actually, with donkeys, that supposedly works because they're animals, they have brains, and they do something quite different than just a magnet. The German culture people will know this Lukas, der Lokomotivführer. You know this story, or is it already ancient? Maybe some people still know it, where they have this invention where they mount a magnet on the locomotive. And the locomotive can then fly following this magnet, which is attached to the locomotive. And we all know that doesn't actually work. And part of it, why it doesn't, that would violate energy conservation. That's sort of the physicist's argument. But the other thing is that the equation of motion that you would write down where that magnet is a force on the vehicle is actually not the correct equation, because when the vehicle has moved a little bit, the magnet has moved again. So the equation that you wrote down isn't actually describing that system. Because in that equation, the acceleration at that next position would be given by the function of the magnetic field, but that's not actually what happens. And so here it's instead of a carrot, it is something disgusting, let's say, that would repel. And again, that shouldn't really work. That is, if the vehicle now rotates on the spot, these forces move with the vehicle, right? And therefore, the dynamic system isn't as described as the shape describes. It would be the shifted dynamic system. So why does that work? And I illustrate that here, in which the vehicle is just rotated, here. Between this and that is just rotated on the spot. And so that shouldn't matter, right? So what I should have is that when it was here, I was at some angle, let's say here, and this curve should tell me what I'm doing, turning away, let's say, from this obstacle. And when I'm at a different location, I'm at some other angle, but it should be that same curve. If it's not the same curve, then the dynamic system doesn't actually describe the future. Then it is, it's actually not clear what that even means in dynamic system. As you see with the naked eye, the black curve is somewhat similar here across these two things, but maybe we just made a mistake. Yeah. Yeah. Now I'm actually here. I just this vehicle hasn't rotated. I'm just illustrating what the problem is. But sorry, a little bit later, I will actually really look at what happens when the vehicle rotates. So here is one situation, right? This would be the red line. I'm here at this location. The 2 sensors see this. And now I'm shifting the heading direction and really taking care of, or taking into account that now it's different sensors that sense the obstacle. So here it's sensor 4, 3, and 2, I guess, who fall into this range. And you see there are actually 3 contributions here to this to the forces, and you get this supervision curve, and you'll sample it at this location, which is different from what you had previously. There were these 2 sensors and these 2 contributions. You were sensing it at that location. Now, pay attention to the black curve. And the black curve is actually, as you see, somewhat invariant, right? The repeller here is lying in the near sensor 3, which is pretty much vertical. And here the attractor lies between sensor 5 and 6, so also pretty much vertical. And so the superposition is actually invariant. So why is it invariant? Because it actually senses the environment, and the sensor information environment has changed, and has changed to essentially keep the effective repulsion invariant. So this would be not necessarily true. You have to actually arrange for the force that is on to be right for this to be true. And actually, in this approach, it's not exactly true. It's only approximately true. And you could mathematically determine the width and the distance depends of these forcelets in order to make it exactly true, which would and have to make some assumptions about the obstacle. So it's in that sense also a heuristic approach, but it actually turns out to be very robustly the case, and that you can really just take reasonable values for these parameters and always find that it's approximately invariant. And that's why that works, why that approach works. In the essay, I invite you to think through that a little bit more. And it takes a little bit some thinking to understand that fully. This is a very typical problem that arises in programming vehicle path generation. When you do potential field, you have similar problems. And actually, students often make a mistake when they program that the first time. One of the symptoms when you make a mistake is that the robot might start to rotate on the spot because it gets some repeller, and the repeller moves with the vehicle if you don't do that right, and then it just keeps rotating. And when you have that, you can easily say, you must have made a mistake about the coordinate frames. This is also one of the reasons why we're having these psi variables, right? Here, I told you on the vehicle, we don't even compute phi. But to understand why it works, we actually need that framework. If you were to take the variables to be in vehicle coordinates, and you can see then something like that could exactly happen, that you always turn away from the 30 degrees, and the 30 degrees rotates with you, so always turning away, so we keep rotating on the spot. Okay, good. You can look at these slides. I went through this a little bit quickly. With my bad vision, I have a hard time tracking exactly what's on the slides. Okay, so that's the obstacle avoidance. The target acquisition is actually unchanged in these examples. The book chapter just assumes that we know where the target is. In many of the applications, the target was fixed by dead reckoning. That is, we assumed there was some initial position, we assumed there's a coordinate frame, and we programmed into a robot the target is at these coordinates, so in X, Y, from world axis, from its heading. And then the vehicle kept track of where it is by adding up the commands to the wheels, essentially phi dot, right? You also need the speed, of course, the forward speed. And you just add that up. If you have servo motors, it's reasonably good. And then from that new position that you estimated, you compute the orientation to the target that you initially gave. That is something that will drift over time as you make errors. So it only works for a short range, but that's a typical approach. And that is actually something that humans do. I'll talk about that in navigation. You can actually close your eyes and then make a few steps and approximately know where you are. And it's quite intuitive. If you do that for a very long time, like keep your eyes closed for a very long time, then your estimate of where you are will get worse. And it's actually well studied. And a lot of engineering processes use this sort of thing. SLAM, somebody mentioned that earlier, is a method that uses this in part, sometimes called path integration, where you're integrating your current path. And that's how we did the target in these examples. We actually, in these projects, provided a whole perceptual system to detect targets. I'll show you. I wanted to actually show you. No, I won't actually, but I can ask Lucas to show you an example of a video. I'll point you to one where we use, for instance, vision and use a colored object as the target and things like that. So in other words, the origin of this term is a bit different from the origin of that term. That has real consequences when you have the target from a sensor like that. You really know the side of the target. Then you actually need to know phi. just to estimate where you are and compute the target contribution. The obstacle avoidance as such doesn't need that. And yeah, then you can actually go through the whole logic that we previously expressed about, you know, when constraints are compatible or not compatible. Now you go there just as a result of this low-level sensor information. So for instance, we'll be going through the bifurcations when the distance between two obstacles increases, really just based on the pattern of sensory inputs that you get. You know, when it's very wide, in this case, you have only two sensors to contribute. And so this is the obstacle contribution. You see there is it's sort of a light gray. There's this one sensor and this six sensor, and they are far apart from each other compared to the width. And you see that in the middle, they don't overlap very strongly. So if you put a target contribution on top, this is the sum of all of those that can overrule. You still have an attractor here in the middle. Actually, between the two repellers, there is already an attractor, sort of the attractor from the side, right? The one force that goes repels, makes a repeller here, the other there, and there's an attractor in the middle. So if you add the target, you have a nice attractor in the middle. You go through. And here, these are shifted closer. There are actually now four sensors that contribute. But even if you look just at the inner sensors, which would, the ones with, no, the inner sensors, 5 and 6, 5. This is 5 here, and where is 6? 5 and 3, sorry. 5 and 3 are the inner ones. Here's 3 repeller. Here is 5 a repeller. See, these overlap, they make a repeller overall here. When you add the target, you cannot overturn that. In fact, it's because the target contribution is always weaker. We make the target contribution have a smaller slope than the obstacles. So the distance between this and that is, the difference is that there's a single repeller here in the middle. There's an attractor in the middle, and there's a repeller in the middle, right? So you're going around the two obstacles here, and you would be going between, right? We can figure out exactly at which that happens in order to do this right. This is an example of figuring out this attractor landscape as you parametrically change the distance of the objects, and that's how you can actually do the parameter tuning. Make sure that that happens at a reasonable distance between the obstacles. This will depend on, you know, how strongly the strength falls off with distance and the sigma parameter that you have there. So here's an example. This is the robot. It's about 40 meters. There's a person walking into this. You see the scale. These are like you know, the storage devices for folders. So it's about this size. Vehicle is about 40 degrees. The keyboard is actually just put on top. It's not really part of the robot. Later we bought an infrared keyboard. Initially we didn't have that. There's this computer screen. There's a computer here in the middle. It used to be. It was an embedded computer at that time. This was in 1990 something. So it's really ancient. A PC with DOS. There was this operating system DOS. It was a terrible nightmare to get all of this to work. And this became Ali who actually built that robot. So these sensors are here. These black things are actually sonars, which we use for some other projects. The sensors are just atop the sonar. So these little white things atop the sonar. There are actually other things here on top, microphones. We did actually for Texas working to sound sources. And I showed that, I think, in the winter semester. And there are 2 servo motors on the bottom. So this white thing is really just a mechanical mounting of the sensors. And the radius of the vehicle is computed from there. So now let's actually really look at the content. So far, I only talked about what the vehicle is like. So here, the target is this cross. This is by dead reckoning. We find that in the robot computer. See, it turns around only as it gets close, because that's when the sensors start sensing. And then it ultimately starts turning back to the target. And see, it doesn't know, you know, it almost cuts into the object. Only when it gets close does it get repelled again. It's not global plan. Right? It doesn't know there's an opening. Just by chance that it turns that way and that it finds the target. Here we made a little opening, and still, actually, you see it slows down, and we actually had a velocity control that I don't explain here to that. See, here it turns in the wrong direction, and Pierre Mallet helps a little bit, although ultimately it would find its way. I'll show you some other videos later. And you see, even hits the obstacle, and then ultimately it finds the opening, just because there is one. If there wasn't one, it would be always just rotating around that. And then, oops, sorry, I wanted to actually just move a little faster to this here when we ultimately open it more. Here. So now it's open enough, and you see now it goes through, it actually oscillates a little bit because it loses the sensory information from one side as it turns a little bit, and it turns around that way. And that's sort of demonstrating that the bifurcation really works in the hardware. Yeah. And this is in the paper, you can have a look at that. This is really looking at different moments in time. The interesting thing about that is, I invite you to analyze that in the essay, that you can see that because of this nearsightedness, the system really goes through the bifurcation in time, because initially it doesn't have any obstacle contributions. So there's an attractor in the middle. And then when the obstacles come in, the repulsive forcelets grow. And then at some point they overturn the attractor and make the repeller. It's not exactly the bifurcation. It's not the same bifurcation as a function of distance between two obstacles. It's a bifurcation as a function of the relative strength of the obstacle contribution. It happens in a small range. These are different positions, different moments in time, you see. And just between, this is only an obstacle contribution, only a target contribution, no obstacle. And then there's a little bit of an obstacle contribution, but still, there's still the target contribution still dominates, still an attractor negative slope here, but it's getting flat. It's closer to the bifurcation. And now it has happened. Now we have a positive slope here, a single repeller, and there are two attractors on the side, which correspond to turning around. So I'm inviting you to really look into that in your essay to really understand it. And you can do similar analysis with this opening and so on. This is another, you can actually also look at how it tracks the attractor as it moves. I invite you to do that in the essay. And here's an interesting graph where in this first example that I just showed you, when you get close to the wall, it tracks actually the attractor states in the dynamics. This is a function of time, and essentially Stella had all the data. Of course, we stored the data on the little, this had a solid state memory we're very proud of. Now every laptop has that, but at the time it was a huge effort to store this in real time, because you can't have a hard disk on these robots because they have no damping, so it's too much vibration. The hard disk would always break and so on. At the time, it was a big effort to get that to work. And now my laptop has a gigabyte of solid state memory. At the time, I think we had 120 kilobytes or something, and it was very costly and difficult, and DOS didn't speak to it. So I really learned all this technical stuff. And only our research engineer Pierre Mallet was really, without him we wouldn't have managed to do this. Or Estelle is also an engineer. She's funny. So as the vehicle approaches this wall, it goes straight because it only has the target contribution, and then the sensors start up, and you see, in a sense, you see the bifurcation. The attractor splits into two attractors. I should say, so on having the data on the robot, you're able to compute the fixed point, right? Just from post hoc from the equations, and that's what is done here, right? And so you see there the split. There are two attractors now outside. The solid line is the actual heading direction the vehicle takes. There is a repeller here in the middle that's not shown, that one could actually also compute by inverting time. You see that it does take a little while before the heading direction actually switches to one of the attractors. That's because there is the repeller is a fixed point, and it doesn't have a lot of rate of change. So it takes a little time to escape, in a sense, from that repeller. And we actually added noise to our control system to escape from the repeller a little bit more reliably. So that's sort of a critical thing, that you don't do that too long. And then it actually goes to one of these attractors, and And sort of as it turns around, the input again changes, and it tracks that attractor, then moves again, because now the obstacles are left behind, they get weaker. Ultimately, it sort of comes back to the angle that points in the direction of the target. And as you see, it does track that. Again, it has some delay, like the repeller moves a little bit more quickly, fluctuates a bit, and the vehicle sort of smooths that out because it just doesn't follow that instantaneously. And the other curves refer to other situations. So again, in the essay, I invite you to look at that, to study that, and write about it. Okay. So I'll just show you a little bit some demos about that. So this is the same system, and we just show a few cases. Here's the starting point. This is the program target. And as you see, it does that very nicely. Of course, these obstacles are done, white colors with very good detection for the distance sensors. So it's a very nice kind of setting. So it does that right. Okay. So see, it does find the opening, but really just based on local thinking. So it's just that in the world, there are these openings and continuities. So this is the reverse. It's supposed to go in here, and it will find its way around. So it looks like it's following the wall, but it's really just obstacle avoidance. It's always trying to turn toward that target, and the obstacle avoidance pushes it away from that. And it ultimately finds the opening. I'll make an argument about that in a moment. I'm showing that for a reason. And in fact, it turns around and then it finds that opening. Doesn't know anything about openings. So it's always trying to turn to the target. And as there's an opening, the obstacles don't push back so strongly, and then it can break through. Not kind of interesting. And here now we close that wall, close that opening, and then it takes the other route. Now it doesn't actually know anything about these routes, but just emerges again that then it will be going in this way. And also finds its way in there. Good. And so we actually really exploited that. Did I put the videos in here? So we built a wheelchair. Actually, Pierre Mallet was personally motivated. His daughter was using a chair like that, and unfortunately she died later. She had a neurodegenerative disease, a typical kind of people who might want a wheelchair like that, because if you have motor control, you don't want an autonomous wheelchair. But if you have a motor problem with due to some neural problems, then you might not be able to do this online control of the joystick. And sometimes you still can have intermittent control. That is, every now and then you give a new target to the robot. That's what the system was like. The system would always have a target that was a few meters away, and you could update that, but at discrete time. Whenever you have a chance, you can have different interfaces for that. And it would be doing, just move to this target and just do obstacle avoidance based on a lot of these low-level sensors. See, there are these sensors. They were mounted all over the place. We had dozens of those sensors. And it's a more complicated thing because this is a vehicle. It doesn't, it's a car-like vehicle. It doesn't have this on-spot rotation. So there are some problems with that. But it worked extraordinarily well. I don't know which videos I have here. And so this was actually in our lab space in Marseille. I think maybe this is not the one. It's just indoors. But I have ones here. I think this is one where it moves through some corridors and goes through doors and so on. And so this would be able to navigate quite reasonably in such environments, which are the typical indoor environments, because of the nature of the environment, right? It has these walls, and it will be doing this wall following. And as soon as there's some opening in the wall, it will go through that opening if the obstacle pushes this way. So for instance, if you wanted to go into a room, you would just put the target inside that room, and it would be driving along the wall until there's a door to that room, and then returning. So even though it's very local, it's just local, extremely low level, very stupid, emergently it does something reasonable that almost looks like planning, but it doesn't really need to navigate. So this system does not actually really know where it is. It doesn't have a map of the environment, doesn't build a map of the environment. There have been a lot of autonomous wheelchair projects that were all aimed at making SLAM, by building maps and doing global planning better maps, which is much more effort. At the time, was totally out of reach. And even today, there is no system of that nature that works. And so this is really, really much more simpler. We actually did test that system with patients. We had access to a clinic near Nice that was specialized in people with severe degenerative motor diseases, and they were the kind of people who could not control a joystick. You know, in reality, people in these kind of conditions sit in their wheelchair until someone moves them, right? In a clinic like that, you can imagine maybe every couple of hours somebody will move them a little bit, but other than that, they are totally non-autonomous. And our wheelchair just allowed them to move a little bit, right? They would be just going in the area they are dot around a little bit. And it's just not able to do. We actually had a little bit of a sensor that detected stairs, so we detect whether there is something going down, again, just a distance sensor, so it would not fall down the staircase. So it would also avoid that as an obstacle. The patients really loved that. It was really just that little contribution to have a little bit of autonomy. It was absolutely impossible to make this a product. This is a very interesting insight we had because of market issues about how many patients. And there's one company worldwide that controls access to the bus that is on these electric wheelchairs. It's the same as in cars. It's a doubled CAN bus. Some of you might know CAN, and has it's a redundant CAN bus. And the company is actually called Dynamics or Neurodynamics. No, Dynamics. I think it's called Dynamics in New Zealand. And so this company, you have to register with this company to get access to the bus, and they require something like between 1 and 3 million to just for that, to support that. And so you need to catch somebody to give you that money. And then the other issue is which health insurance will pay for that. And that is essentially impossible. They have a very interesting pricing model where to recover the cost of the initial investment, they make the individual contributions extremely expensive. So even though this would, in terms of, if you build a prototype, it costs perhaps 2,000, but they will charge a lot more to recover the development cost. And then, if you have only maybe 1,000 patients in France, it's impossible. So we never made a product out of that. We had a grant to push this to the next stage, and yeah, we had a nice demo. We wrote some papers, but it was impossible to move further. It was very insightful for us to see how that happens. And the same happened to all the other projects in this area. There is today no autonomous wheelchair. There's been much more progress on autonomous vehicles because of the market situation of that being so much more attractive. So it's also interesting to understand. It's not just technology. And this was the best shot because it is so simple and thus not expensive, but there's still enormous market problems. This little side note. This is the one I wanted to show you. So this is like the high point. This is a paper that I actually used to have students study, but ultimately understood it was too complex. It's from 2019. This is the Stellas group in Minho, and they have pushed this very far. So these are 2 robots that are sort of like this one, but much better modern versions. And they developed an approach how just scaling up this thing, how the 2 cooperate. So there is some following behavior. So the one in the back follows the one in front, and they both do obstacle avoidance, but there's also some other contributions, just forcelets to the dynamics that make that the one in the back is a sort of makes an intermediate point so that it when the first one avoids, it doesn't cut into the obstacle. It sort of goes around. This is quite ingenious. And as you see in this demo, I'll go back a little bit because there's some interesting parts here. As you see in this demo, you get the online updating for free, right? When there's a new obstacle, it's all just basic constant information. So it's absolutely capable of dealing with time-varying obstacles, right? And there could be, for instance, humans that walk around that. See the red thing he's carrying around, that's the target. So they have a little camera there, and the camera goes for something red. And so it's just for the demo, it's just moving that around so it follows that red thing. And so this is the load that is being transported. This is, of course, the laboratory demonstration. They have actually collaborated with a German company that has a plant in Braga, where they brought that to the factory floor. And they've been working, still do that on all kinds of technical issues. Again, there's a lot of other non-scientific stuff that you have to do right for that, like to the overall flow of this. There's published papers now on how to organize that. This is sort of the academic paper about that. Yeah, there is a line of thinking like that. There was earlier work by someone called At Large, who used our approach to do to organize flocks, multiple robots. And Estella had a student, actually, this guy, I think it's Montero, Sergio Montero, who earlier worked out how to do this with like arbitrarily many robots to do formations and have flocks that break up into multiple robots. You can do all of that based on dynamics. Good. That's that much about this simple part. I want to spend just a little summary here. I want to do another little module before we close, which pushes this one level further. And this is something actually we did even before the robots I just showed you. And that's sort of, it's a little bit harder to understand potentially. And I'm not asking you to understand that in detail, but just maybe see, this is really attractor dynamics thinking. It's more radical. I'll present it to you and then we'll see what we're doing. So this is an even lower level system. It doesn't have any dead reckoning. We totally hope this is really a Lego robot. This is what it looks like. It was a wooden platform. We built the hardware even from scratch. So there's a wooden plate. There are two motors. These were originally like toy plane motors, like servo motors, but we cut off the servo part. So they are unservoed velocity motors. That's kind of important because it means that they are not, it's not guaranteed that they take on the velocity that you ask them to do. And therefore, you will have to use the dynamical system, the planning part, as part of the control. So that if they move more than you want, then the target moves, let's say, more than you want, and it would update the dynamics based on that. We plan as a form of control. And so the motors are below that. You don't see that. It has here these same kind of sensors. If you see this black thing is the emitter of infrared light, and this little a cube here is the detector. And the black thing is actually a rubber we put on top to control how the spread of that infrared light. When you do this, you have to address these different sensors in sequence. So because only one is to be on at a time, because the reflected light, and you have crosstalk among the sensors, right? So that's actually the limitation on how fast the sensing is, because you have to have a little window for every sensor to take a reading. And this is just the batteries and the cable created the cabling, like the like prototype kind of version. And so what there's something else here. It's literally Lego. We use some Lego here. And on top of this, there is another sensor, another one here on the right. It's a so-called LDR, light-dependent resistor. So it's a resistor whose resistance can be modulated by light. It's a photoreceptor on top that does that. And that was how we got any kind of target information. So these would be the obstacle buttons, and then this would be target information. And nothing is calibrated. It's all ad hoc. So it will only work if in closed loop, any error is being corrected by updating the plan. So how this is different is that now we cannot actually rely on that reckoning, knowing our, that the motor command would really generate the heading direction. And so the only thing that we can do is make sure that the real heading direction doesn't drift too far away from the hypothetical one the dynamic system presumes. I'll explain that later in more detail. We will not be able to put a target into this by dead reckoning, right? And so how do we get very low level information about targets? Well, the idea was that we just control the speed of turning, the turning rate. And we will say when we are on track, the turning rate is 0. The attractor is 0, we go straight. And then we say if the target is on the left, we make a turning rate to the left, some arbitrary value of turning rate. And if the target is on the right, we turn to the right with some fixed speed. And then whenever we think now the target is close enough, we switch to going straight. So we don't have to know exactly where the target is. We just have to know if it's to the left or to the right, or have some zone in the middle. And that was based on, do I have that in text? It was based on these two light sensors. Essentially, the light sensor votes for the direction on which it is. So the left light sensor always makes a attractor of turning left, which would be a positive turning rate. And the right light sensor makes an attractor at negative turning rate. And you add those, and if the two have the same light strength, then they would average to 0 in the middle. And otherwise, you would have an attractor on the left or on the right in turning rate, and in turning to the left and the right. So here's a example of that. Sorry, I discussed the. I should actually discuss the attractor first. So the turning rate, that's phi dot, right? The derivative of phi. That's now our dynamical variable. It's one derivative higher. And so this is the rate of change of the turning rate. That will be angular acceleration. So it's also a dynamical system, right? We just call that omega, let's say, the turning rate. That's our dynamical variable. The new exercise sheet that you're handing in today actually plays with that, right? Some of you have already probably done that, and you see that you can just treat the derivative of heading as another variable. And this is the case where we do that. So it's a second order equation for the original phi, but we'll throw away phi. We'll only use turning rate. So this is the acceleration, the derivative of turning rate. And so the left sensor, both the two attractors contribution, right? The left sensor and the right sensor make two attractors, and they are broad, the sinus curves. And so when both of them have the same strength, then we will have an attractor in the middle. So this is the case where the exact same strength, the attractor is really in the middle. And here's the one on the right has a little bit more strength than on the left. You have a turning rate that's a little bit off to the right. So the strength is just modulated by how much light you detect. So if you have the same amount of light left and right, you go straight. And if there's a bit more light on one side, then you're going to turn to the, so we make sure that the turning rate is then in the direction of where there's a bit more strength. So that's uncalibrated, right? It just needs to be some limit on how, you can imagine that there can be a limit on how for that to be stable, right? If it's, you could have that it is not enough to really turn in time, there will be a too weak dependence on light distance, or it could sort of overreact. And you have to control for that. And that ultimately depends on your forward speed. You have to make your forward. If it goes slowly enough, it will be stable. Okay, so that's the motivation to go to this higher level, that to get rid of this whole idea of, so remember, most robots have a map, they know where they are. With the previous robot, we just trying to say we only know where we're heading. That's one derivative higher. Now we don't even know that, we just know our turning rate. We don't even know where we're heading. Huh? This is really one derivative higher. Now, how can we do obstacle avoidance for that? And this is the idea. So this is now saying, okay, we'll have some kind of bifurcation logic. And the idea would be that for that turning rate, we can either have a turning rate for going, for not turning at all, so 0 contributions to the turning rate that is stabilized is going straight, 0 turning. Or we turn to the right, so I have a positive rate of change. Actually, again, switching, which sign it is. When the obstacle is close and it's to the left, right, then we want to turn right. It's close enough to care about it, or vice versa, right? If something is close on the right, then we want to turn left at a certain rate. So these three kind of things have to be done. Each of these can be done with, let's maybe first discuss the conceptual example. I'll show you the equations in a moment. So this is the dynamics of turning rate for that. So again, turning rate as the variable, this is the derivative. No obstacle, we have an attractor at 0. And now this will be an example, there isn't an obstacle, and the obstacle is exactly at, so it would be, we could either turn to the left or to the right. And we have two attractors, one for turning positive turning rate, one for negative turning rate, but definitely going straight is a repeller. So you don't want to go there. And now this will be when the obstacle is on the right, and it is, close enough to matter, then we would have a turning, imbalance that is the attractor for turning to the right, to the left, turning rate positive is turning to the left is stronger than the one of turning to the other direction. And if it is really close, then we don't want to have that alternative at all. We'll only have the attractor of turning around it to the left, and the other one will be gone. And there's a symmetrical case for the other side, right? And so ultimately, this leads to this kind of diagram. So if you're now thinking of your heading, and there would be different zones here. There would be a zone. We're thinking about the obstacle, what the obstacle does for your heading, and there will be that if there's no obstacle, the obstacle is far, then we want to make this an attractor. It will be an attractor in the middle. If there is an obstacle close and we're heading exactly toward the obstacle, we want to have that decision that is either go right or left, but don't go straight. If the obstacle is on the right, I have to see if I switch left and right, but let's say it's on one side and close enough, so no longer this distance, close enough, then we want a attractor at the side, appropriate side to turn away from that obstacle. And on the other side, we want to have the other attractor at this one. That would be our phase diagram. And so if you see this immediately, this is a mix between a pitchfork bifurcation and two tangent bifurcations. So if you go from here to here, that is, the obstacle is right ahead, and it's just initially very far and then comes close, then you go from a single attractor to a repeller with two attractors left and right, and that will be a pitchfork bifurcation, the one you have studied already, but it's not for turning rate. While if you look at this, going from here to there or from there to here, that would mean if you have a obstacle right ahead and you're moving it, let's say, to the right, then one of the two attractors becomes unstable by colliding with a repeller. So you could think of this transition as this attractor and that repeller colliding, like lifting this up here and colliding, and only this one left. And similarly, on the other side, it's just the other thing. Like if you do this one, the attractor of turning in this direction would collide with the repeller and be gone, and only the one left. So you're combining the tangent bifurcation with the pitchfork bifurcation. Now we took a particular mathematical form. That form is written down here, and that uses particular notation that we developed. And you recognize perhaps a few things. Omega is now the dynamical variable. Omega is the turning rate, right? That's our dynamical variable. So the dynamics of omega is omega dot is some function of omega. And essentially here you have this normal form of the pitchfork. This was on the first exercise sheet. Now, it was called x and x to the third. Here it's omega and omega to the third, right? Remember, this is minus omega to the third. That makes this funny function here. This is the minus omega third. And then the omega can be, if alpha is negative, it makes this sort of thing. If alpha is positive, it makes that sort of thing. So this bifurcation is from this normal form here. And this is really just a fancy notation for a constant that we add, a constant as a function of omega. Right? It doesn't depend on omega. It actually turns out it depends on heading, and ultimately depends just on sensor information. So this is a constant, and the constant is such that it's 0 when the obstacle is right ahead, and it is negative when it's on the left and positive when it's on the right. So it will shift the dynamics up in one case and down in the other case. And we actually computed it from our force sleds, right? We have these obstacle sensors, the same one we have before, you know, the sensors on the vehicle are the same one as before. So we can get from that these obstacle contributions. It will be a single obstacle contribution, but then we have the superposition of all of these. And they, in a way, tell us where we are relative to the obstacle. They say, you know, where that obstacle force that is positive, that we're on one side, and we're saying that we're on the other side. And if there's no obstacle there, or it's far, then it's flat, you know, then this will be zero. So we can use this to both detect whether there's an obstacle there or not, and also to know which side we're on. So there's just some mathematics to do that. So we're transforming this by you know, sort of by squaring it, or some, we call it the potential sum formation. We can just detect whether there's an obstacle at all. We did this with this alpha factor, just compute it, integrate this, you get that. Oh, sorry. You integrate this, you get that, and then you take a sigmoid on that. We use the arctan, and that's just an indicator function that is in these directions there is an obstacle is relevant, in these directions there isn't. And then we can use the sign of this to determine whether we go up or down. And that is ultimately what goes in there. So the alpha was computed here from this sigmoid, and this is to control the sign. So we're using here this for the sign. There's some normalization. The pi is just because of the nature of the arc. So this is just one way to engineer that. And you remember when you have a the normal form of the tangent actually has a second order equation here, but this also works. That is, if you have a nonlinear form here and you add something, you remember the tangent bifurcation, it was just a constant that pushes you through the bifurcation, constant added to a nonlinear form. And that's, you know, this constant actually controls that tangent bifurcation, but does it for the pitchfork normal form. So that's how this was done. I know it's just, I was just, you have to understand the detail, but it is sort of engineering with bifurcations, right? You can see that's sort of the logic of that. So what that works amazingly well. It's just add everything. Works amazingly well. So in the final equation, you don't need phi. You don't even need, you have an inner variable omega that you compute, but you don't need phi at all. And what you do is on the robot, you just have the numerical solution of that equation. That is, have some inner variable omega. That omega, you know, is the turning rate, and from that omega, what you actually really need is the current state of omega that will determine the difference in speed to the left wheel versus the right wheel, and you actually just give some voltage and some factor. You don't know the exact omega, it's just some factor. It has to be close enough, some gain factor. And you also need, of course, to know the sum of the two speeds. That's the speed with which the vehicle goes. We actually kept the constant in many cases, which is some other constant there. And therefore, your equation just is an equation that all the terms that are listed here, that you have to program them on the robot. This was a 8-bit processor. This is actually, we always said Coca-Cola machine chip. So today, actually, even a vending machine has a better computer than this. And so we had, I think, 120 lines of code. It was interactive C, some kind of special program for that. This is the chip that is still, I believe, or some newer version of that in the Mindstorm, the Lego robot. So at the time, MIT had a kit that you could buy with that programming language and that chip, which was used for robotic lab classes. So we bought one of those. We had very low budget, and we used their compiler and so on to program that on that chip. So it's not a regular computer, right? It's a microcontroller. And we just had some electronics that Pierre Mallet built for us to transform the signals. We had the analog signals into something this chip would take. We called this guy Rodinsky, and it worked amazingly well. This is from a paper, and here, this video should be working. Yeah. So this video should start. Why does it start? Do I have to click on it? Ah, yeah. This is Stella Bishop, by the way, at the time. She's now a little older. So here it's just driving around the lab. And the ambient light is, some reflecting light, so a small contribution. You see, it's quite agile. It will be turning quite quickly because it has the second order dynamics, goes around. Its speed is really only limited. Could drive my chart. Speed is limited by how quickly the processor can update the equation. This was the bottleneck here on this robot because the chip was so slow. And it does a very agile. And now we turn on these lights because this is strong light and it will be orienting to those lights. And we'll see it's going here, going to, and it stops because we made the speed depend on the total light intensity. And so it looks like it's interrogator standing there, and then it turns away. Almost looks animal-like. But it was just a switching on of this light that made that, and so on. And she ultimately comes back. Doesn't have a sensor on the back, so it takes some while before it gets that grading again. We'll go there again. It was really very cool. So we went with this robot to a competition in Italy. Forgot the exact name of that, where it was about behavior-based robots, very low-level robots, and it was actually a workshop where students were working on projects and so on. And the interesting thing is, all of these were small vehicles, and we worked in different groups, and many of these were on tables even. And then, they all had their algorithms. And then we were supposed to do a demo in a different room downstairs. And we even had a TV team it was actually in Switzerland, the Italian-speaking part of Switzerland. And there was a Swiss TV team who were filming that for some kind of, I guess, probably not for mainstream, for some youth programs. And they had these strong lights, these TV people always have these strong lights or something. And all these low-level robots have sensors, low-level sensors, and that means they don't have a lot of invariance. Yeah? And we humans have this invariance. I mentioned that earlier, but you don't probably know about it very much. And we can perceive the environment somewhat invariantly as we change sensory conditions. For instance, I could change the lighting in this room and you would still see the same shapes, and you can still estimate distance and so on, because your perception system is amazing like that. I mean, the invariance under change of luminance level in the human eye is amazing. 6 orders of magnitude. For instance, did I mention that before? I sometimes say that. So for instance, here in this room, the window is probably, there's no sun now, but it's several orders of magnitude more luminance there than in some shady area here at the bottom. And you can actually see contrast even in the shady areas while you also see the windows. You might be aware of that difficulty if you have a camera, even a digital camera, where you often see that when there is something bright, then the rest is just black. You don't see any contrast in there. And actually now, like the iPhone one has a digital emulation of this, and actually is quite good in making some kind of local invariance extraction, while classical cameras are terrible at that. And so that's just the lowest level kind of invariance. And we have much more sophisticated forms of invariance extraction. So if you have low-level sensors, you don't have that, right? It's just crude sensory information. And so what happened is that when the robots were transferred into the studio environment, after all this tuning that was made, pretty much none of them really worked. And they all did something odd, except ours. Ours worked extremely well. This was cheating in the sense that the main contribution was infrared based, which but it's also very robust. It really doesn't depend much on that. So it was happily moving away, and we got into this Swiss TV program because of that, because it was still moving. And the other interesting thing is that all the other robots, many of the other robots, got stuck in corners. Ultimately, and some of them even formed corners by collectively, like one, another, and then they built a corner for each other. And that is sort of generic, and it's kind of interesting. Behavior-based means you have this very local rule of how you do that. Ultimately, if you program a robot yourself, you can try that if you have a Mindstorm, the natural thing of how to think about that is the caricature of what I was telling you about, where we would say, well, if there is something close on the right, I want to turn left. If there's something close on the left, I want to turn right. Pretty much all the algorithms they had were some variation of that, some using neural networks and some using other kind of math, for fuzzy logic, and all kinds of approaches. But the functional idea behind it was ultimately that. And you can see that that can create an attractor in a corner. So if you ultimately in a corner, you can see it can be some funnel where as you're turning left, this wall comes closer, turn right, that wall comes closer, you converge into the corner. And that is actually what happened in a lot of cases. And you have to tune it specifically to not do that, right? To make sure that the rate of turning and the rate of advancing have the right ratio for that return. I'm telling you a little bit of story about that, that this is the behavior-based robotics approach has this spirit of not being exact, right? It's heuristic. It's not guaranteed to have the right solutions, and that can work quite well, but it does struggle with this level, this problem of invariance. And our approach is not theoretically exact. It's still heuristic, but it is more robust. It has a strong level of invariance. That is ultimately because it has a real theory. This mathematical framing behind it says if these assumptions are right, which is that the invariance of the dynamics, as I hinted, is correct, the same problem arises here, approximately correct, then it actually guarantees that it has the constraint satisfaction that the attractors of this model enforce. Okay. So the cool point about this is, previously I said, why do you actually generate interesting behavior while you're sitting in an attractor? Now, the logic was, well, because the environment makes that as I move around, the attractors change, distances, angles change, and therefore the interesting behavior arises because that sense information changes, the attractors move, and I'm tracking these attractors. My velocity variable makes that possible, and therefore it's the complexity of the environment that leads to the behavior to be more or less interesting. And if there's the environment is very boring, we'll just go straight. And now here's the same logic, but one level higher. So this system is sitting in an attractor with respect to turning rate. And so as it turns, it goes through bifurcation. The turning rate is an attractor, but that means it is turning. And as it is turning, one of those bifurcations happens. It has a new relation to the obstacle. So the terms of the equation will change, goes through bifurcation, and that changes its turning rate from 1 to 0, and we'll start to call it straight line. That's being one level higher. So it makes it very agile. But we use this approach in a collaboration with a South American student here for to control drones. And we only did in simulation here. We didn't have any drones. He moved back to Brazil, and he did some drone work, but actually it never really was reached any published level. So they have somehow different. So it never led to any. We published a version of this in the simulation, but we never published the actual drone version. It was the idea that it would be very agile thing. So I will be interested to see that. I have since given up working in this area because it's sort of too mature, but it was really fun. Okay, the summary, just for the record. Certainly, these last examples show you that you can get this cognitive-like stuff, the decision-making bifurcations are now really in time as you turn with minimal requirements for perception. That's certainly true, right? So certainly the extreme of that, I don't think one can push it further. That's probably the most lowest level we ever had. Good.